We are discussing about the diagonal relationship here. Consider I am having lithium. I have beryllium here. Boron, carbon is there. So here I have magnesium, I have aluminum, I have silicon. I have nitrogen, I go for diagonals here. Lithium and magnesium are diagonal to each other. Beryllium, aluminum is diagonal. Boron, silicon is diagonal. Carbon and phosphorus is diagonal. So interestingly, these elements show certain kind of relationship in their physical nature or in their chemical properties. That is called as diagonal relationship. There is a reason why do they show diagonal relationship here. The reason is that they have the equal polarizing power or ionization potentials. So polarization power is given by ionic charge divided by ionic radius. If I do the calculation, I find both of these diagonal elements are having some kind of common things. The values are common, their values are same. So in that case, I call them as diagonal elements. Okay, so there are certain properties they show. Let us discuss about the properties shown between lithium and magnesium. Both lithium and magnesium are harder and lighter. You can see if you put the lithium element on the water, you can see it just floats and starts bursting, crackling on the water. Same way magnesium also does. They are harder as well as they are lighter here. Lithium and magnesium react slowly with water. As you are going down the group from lithium to cesium, cesium is highly electropositive element. So it is the element which will react very fast with water compared to lithium itself. Similarly, magnesium also shares the same kind of a phenomena because of the diagonal relationship. Both of their hydroxides are weak bases. It forms lithium when it is treated with water from lithium hydroxide. Magnesium with water is forming MgOH12. Both are forming hydroxide, but they are not very strong base. You could have seen people using sodium hydroxide, potassium hydroxide, calcium hydroxide. Have you seen people using lithium hydroxide and magnesium hydroxide as a base?
No, ma'am.
No, because they are weaker bases here. And they decompose on heating to form respective oxides. So when I heat them, what will they give? They'll give their respective oxides. Lithium hydroxide, when I heat it, it will form lithium oxide. Magnesium hydroxide also forms magnesium oxide here. Li2O and Mg2O do not combine with excess oxygen to give either peroxide or superoxide. Very important point. See, I have Na2O2. Sodium peroxide is there. I have KO2, superoxide, potassium superoxide is there. But lithium do not form such oxides. Lithium does only normal oxides here. The reason is that the superoxides cannot be stabilized such a smaller size. Because lithium and magnesium are in the second period and the third period itself. As I'm going down the group, the size has to become larger. Only if they are larger, they will be able to bond with oxygen. They'll be able to, you can see for one potassium, there are two oxygens here. Lithium will not be able to accommodate it. Similarly, magnesium will not be able to accommodate it. Their carbonates decompose easily on heating to form oxides and carbon dioxide. And I'm taking lithium carbonate, it forms lithium oxide and carbon dioxide. Similarly, magnesium carbonate, you take it, you eat it, you have magnesium oxide and carbon dioxide. Hydrogen carbonates are not formed by lithium and magnesium because you could have seen sodium bicarbonate. You have heard about it, na? Baking soda. Sodium is forming, but lithium is not forming it. Understood, right? Calcium forms calcium bicarbonate, but magnesium do not form it. Halides of both of them are deliquescent. Deliquescent means they'll absorb water. crystallize as hydrates. You can see this water of crystallization, dot 2H2O, dot 8H. It's called water of crystallization. Both of them are doing, not their respective group members, they don't do that. Halides of both the metals are soluble in ethanol. Halides of both the metals are soluble in ethanol. According to Fajon's rule, what is Fajon's rule? The full name of the rule is called Fajon-Soddy. Fajon-Soddy rule. Why they have mentioned about this ethanol here? Ethanol is organic solvent. Organic solvents are usually non-polar in nature, not like water. Water is polar. Organic solvents are generally non-polar in nature. So Fajon-Soddy says that small cation, large anion, more is a covalent character available. Okay, more covalency is available. Ma'am, where are they talking about the covalency here, ma'am? Let me take lithium chloride, LiCl, MgCl2. It's a metal and it is a non-metal. It is a metal, it is a non-metal. So it should be ionic compound, na? Children, should it be ionic compound?
Yes, ma'am.
Yeah. But I am telling it is not soluble in water. Like dissolves like. If it is ionic, it will be soluble in water. It is ionic, it should be soluble in water, but it is soluble only in non-polar solvent. We are finding out why. It is ionic. It means it should be soluble in water, like sodium chloride. But this is not soluble in water. Instead, it gets dissolved in a non-polar solvent. So Fajon-Soddy explains it. Even though it is an ionic compound, even though the compound is ionic in nature, if it is obeying this rule, small cation it has, large anion it is having, then that ionic compound percentage of covalent character in ionic compound will be larger. So we are comparing between LiCl and MgCl2, which is common. Chlorals is common, leave it out. Consider between lithium and magnesium. Okay? In its group, lithium is small. In its group, after beryllium, magnesium is small. Correct? Correct?
Yes,
So it
ma'am.
is a small cation they are. So therefore, if smaller the cation, more will be the covalent character. If it is covalent, then it will be soluble in non-polar solvents only. So only it is soluble in ethanol.
Master.
The next one, both of them will form nitrites. Very important equation. Both form nitrites. Lithium plus nitrogen also forms nitrite. Magnesium from nitrogen also forms magnesium nitrite. Any other elements of their respective group do not do this reaction. Other than that, very commonly hydroxides, carbonates, phosphates, fluorides are sparingly. Sparingly means mild solubility they show. Apart from halides, all the other things show mild sparingness.